So, friends, this is fifth lecture of the fifth week. That means this is the last lecture of this module, that is prognostics and health management, role of POF in prognostics and health management. And we are discussing a very important component of that, that is Canary and PHM, prognostics. So, first we will introduce what is Canary actually, and its a genesis, and then prognostic distance. What is the prognostic distance? That means I have a canary which is monitoring a component, and what should be the time or distance available, and it is a dynamic parameter that we have here. At every point of time, prognostic is being made, but then the distance between them, that is canary and the main component, okay, it's a distribution, is a very important aspect. Prognostic distance and time to failure. What it means in terms of time to failure, role of POF elements in canary, and then illustration of canary. One simple example we will be discussing in this lecture. So let us say what is the genesis. Actually, in electronic component, this canaries, they find very special application because at microelectronics level, in simple word, we can design a component for monitoring the subject component or system, so that we get a early warning or signal of failure of the main system that we are monitoring. So that is what Canary is all about. This inspiration might have come somewhere or by some personality, that canaries in mines, they provide early information, change in their color, or certain health thing. It provides an indication there are some poisonous gases or hazardous thing are creeping into the mines, and which is a threat for the direct threat for the miners or the workers. They go inside the mines. So this particular canary bird, now this particular system is not there. It was done away long ago, but this was a basically model for having early warning of any safety of miner. Okay. So this is the historical perspective on this embedded approach. Now this is basically part of an embedded approach. That means what I will do is, let's say I am having one component, and there are some nodes or locations on that component. If I can use as a canary, because my selected component and the other components, they are having same structure, and they are seeing the same operational stresses, same environmental stresses. So can I design my canary, that means the component I have selected, to fail early? Now it's a big question actually. My component which I have selected to monitor the main component or subject target component should fail early. What it requires? It requires complete understanding of operational loads, complete understanding the current voltage and other capacitance, so many other things. Then, and second thing is, it should be environmental parameter also. You should know, because I have to create a model, canary model. And then third thing is the material of construction, quality and all. So I should be knowing the complete science of failure of a component, then only I can develop canary. Okay. So intuitively what happens? Physics of failure based approaches become part of the canary, because all the science lies in physics of failure. Maybe on crude level I might design some thinner component. Actually, in industry, certain parts are designed to fail early, and that is basically to, let's say I am lifting some lifting some weight, okay, or and then my I should know in safest way how much it can handle. Or I'll take some other example, that I'm lifting some assembly, okay, and if the assembly I continue lifting it, and if it gets stuck up, my complete system which is lifting it, it might fail. That means the assembly will definitely will drop, which I am lifting, but my system also will fail. So what I do, I create a weak link, physically a weak link, so that if the assembly that I am lifting, it falls, it's okay, but it gets snapped from the main system, so that it doesn't damage the my main system. So okay, so these kind of settings are provided onto the main lifting system, where the hydraulic pressure is put such a way that if the load goes beyond certain limit, the system cuts off, number one, and number two, the assembly, weak assembly which is there, it will also fall into safe place. I mean, it is not something that it will be hazard to others. So probably in mechanical system, these kind of systems are there, but if you have to build into the electronics, you have to understand the complete science. The way you have to understand mechanical engineering, what is the thickness or diameter I should have to snap it. Similarly, we should have all the loadings and everything. It's much more complicated actually. Okay, design. There are three types of POF canary: expandable canary, sensory canary, and conjugate pairs. So we'll see what are these three types of canaries that are there. Expandable canary are devices formed with the structure similar to the. So that means if I have a capacitor, let us say simple, if I have a capacitor in the circuit, and if I provide, just for the simplicity, I'm giving this argument. I have another capacitor which is of lower capacity. Now, obviously, the lower capacitor, if I pass the same current and all, it will fail early. But this will protect my main capacitor which is there on the board. So similarly, this was a simple example. But if I have to really make I have to make similar component, because that component should not play any active role onto the control circuit. So I can design, I can pass the current through that thing, but it will be down the line some circuit will be designed wherein that current will not affect the main board operation and the supply. So if I am feeding 5 volt, I will feed 10 volt or 8 volt for this. Okay, small capacitor, which is a canary actually. So it is something called expandable canaries. Similar component you use as a canary because you want to save a critical component on the electronic board. Sensory canaries, simple, are monitoring devices that track a measurement change in the target system and that have been correlated to failure. For example, an acoustic sensor in the now, you know that any failure, it makes, not always, it makes noise. So if the noise itself, I put a sensor there, I'll know a prior information that when the component was put into operation, it did not have any noise. And noise even in our common life also, we use through our ears. Our ears are sensor and will say there is something wrong. For example, let us say there is a pump operating in the field. So one sensor is I put my hand there and I see temperature. Okay, so I find out I get the advanced information because it is not failed. It is not failed. In fact, it would have continued in this in a couple of days or couple of months also. But a decision is taken to. So there is now same thing is if noise bearing before failure, the vibration level goes up and it reflects in the sensors. Noise, and that noise can be sensed. And in many places they use noise pattern in a particular area. So this sensory canaries, and then that conjugate pairs are sensors that monitor the stress pair whose deviation is established pairing. I have some bearing, I was monitoring the temperature, and one more pair I put it. It is basically having a 1-to-1 correlation, because for bearing I had already had model, and now I put another sensor there. So I got 2 pair of canaries are there to as part of and of course it uses a lot of physics of failure approaches and all that. Okay, so now as we mentioned, we will try to understand the prognostic distance. So first we should understand the definition. Effectiveness of Canary device can be measured based on the how much in advance the alert signals are made before failure of the target system or system component. Of course, deviations are the first signal from normal situation. They are the first signal for a prognostics actually. But one has to be really careful. The not much before, when it is really genuinely degradation has happened, then only it should not provide any spurious signal. Otherwise, if you design a canary which spuriously start giving signal, and suppose in the plant we have canary based maintenance or POF based maintenance approach or RUL based, it will become a problem. So you have to safeguard yourself. The spurious thing should not be there. It should not be too early. It should not be so sensitive. It should be giving it right at the time which is required for maintenance purpose. The difference between the time of the canary device signal and failure of the target system is called, let's say, this is the canary device signal that it is giving, and here it is the failure of the component. The failure of the component and it's a distribution uncertainty, we can say. It is given over here. So what we in normal or Gaussian distribution, we get the 50% at mean value, and here also for failure of the target system it is 50% product and canary. So we got this distribution. So 50-50 PD mode, then 99-50 PD mode. That means it is starting from 99 and it is touching at 50, and PD 50 into 1% it is going, and 99% that means 99% of canary probability, the complete area under the curve. That means you will have a lot of confidence, and here it is at 1% you pick up. These are the options that you have for choosing a prognostic distance. Okay, so I would say that you have to take into failure. Then we have to, if you can use right from here, that means when the problems have just started, and if we can track it, it is a good idea, and it should track up to certain thing beyond this also, because failures have not occurred. It's just distribution. So in the next slide, so what we are talking about is we have captured the point value of the canary failure, point value of product failure, and uncertainty band. You can see here this spread is much lesser, because canary has to be like this, and canary should fail, that guarantee should be there, that canary should fail, should not fail before the system failure. That means there should be guarantee that canary, otherwise if the system fails and canary doesn't give the signal, then it is a complete failure of the canary approach actually. So how to put it on the formulation, So PD is a critical matrix in designing. There is no doubt on this. Another factor is probability that the canary will provide an alert before failure. So this is reliability of the canary. It will provide before the system failure occurs. To determine the probability of a canary failing to provide advance warning of the signal, the sensing distribution of the canary and the failure distribution of the target system can. So that means all these arguments we have used in formulating this formula. That means what is the reliability of the canary? That means canary failure time should be more than the system time. That condition, what is the probability that TC will be more than, T is time to you can say TC and TS denote the time to failure of canary and system. So TC should be more than TS, is equal to 0 to infinity, then PDF of distribution, that is product or system that we are monitoring, and reliability of the canary. And this will give us what is the success of the canary. So you can say where FST is the probability density function of the system and RCT is the reliability of the canary, and we want this situation to take care of our reliability of the canary actually. Now it is quite apparent that if we apply the increasing load, then prognostic distance will reduce because canaries will fail faster. But as we have the prognostic distance loading reduces. Loading could be environmental loading, it could be operational loading, but we have reduced. So prognostic distance has increased. Now PD3, if we reduce the load, like we started from somewhere here, now we are coming and we are coming over here. So PD probabilistic distance. So which situation you will prefer? According to me, I will prefer this particular optimum because I should have time for management. If these two together fail, then there is no use. But it could be optimum here, it could be. So then from this is the gate, prognostic distance is the gate, we can implement, connect our prognostics to health management. What I should say is different component require different time for maintenance. Okay, and that is where I need PHM to give me warning, but at the same time give me some time also. Okay, so we will require a calibration for each component. For a safety component, I will require more time, and for process component, if suppose some component is reaching the time, and if the time it takes for replacement or repair, and if we have redundancy, then this distance is also good actually. But it will depend, it is opening a new gate for health management of the system, and it is a quality or metrics that will be worked out from what is the system requirement, what are the operation manual, what are the design manual, what are the safety manual of the system, that will govern this criteria. And these are all description of the PDs and all that. So canary development, first it is identification that we have done in physics of failure, assessment and sensitivity of the each parameter and all. Then canary model that has to be created, and it is like a physics of failure model created. And finally we have to give time to failure actually. So time to failure model has been created. Then we come to that in canary, it is very important what is the error seeding. That means where we are feeding the error so that it gives, it enables us to design a canary. I am talking about, let us say, some metallization, and I want to put canary because I am operating at the limit of the current permitted by the design value. So I want to monitor it. So what kind of error seeding I will do? I can make a small metallization or small solder and pass through the little higher current and all that. But that geometric error, that process will be called as geometric error. Then if I change the material, and suppose if I have knowledge of material, how at microstructural level it behaves, or inferior or superior, and so then I will do material seeding also. So these are all called seeding. That means parameters that will use for developing a canary. And then load error seeding. Load error seeding, I can increase the current voltage and I can do. So these are the three approaches for developing canary, and probably for any canary development I will use all the three approaches because I want to get the best out of all this seeding that we have over here actually. Like simple example for illustration, I want to do prognostics of a 192 input output ball grid arrays with a sacrificial contact. These are the sacrificial contacts. Sacrificial is a term, it is used in engineering for certain additional components, which like sacrificial electrode. If I put in chemical system, there corrosion will occur and it will tell you how corrosion is taking place inside the system. Okay, so I'll put three component outside and in more corrosive atmosphere. Similarly, here these are the sacrificial component, three at each corner, and they can be utilized as part of the canary. Maybe one, they all three can be put, but this thing should come by design actually, because we saw three error feed. So suppose if I do not do geometric size is not available, material side is error setting is not available with me. If I use 3 only, then what I have is loading. Loading I can increase, and I can fail this canaries a priori before any failure occurs on my board actually. So what I am saying is, even I can leave some contact or transistor, bunch of transistor free for acting as a canary. So it is a very elegant and very effective mechanism. Only thing is how we will tap that, because microchips, they are made of materials. The delamination is not all that easy. So if a company manufactures a transistor or a microchip like this, then I can use it, because they have given some spare thing which I am using as a canary. And these canaries also will be seeing the same current, same magnetic field which is over there and all, but this will give me early information, and that should happen. Then only it will be called as a and for that lot of experimental testing and all has to be done. So this is just example I have given, and then this result of this experiment was the coefficient of thermal expansion for board and component is assumed to be 14 ppm part per million, and that is 10 ppm, that is coefficient of thermal expansion. Okay, how much it expands is that was a factor, and 14 ppm part per million and 10 ppm respectively. Test temperatures were -55 to +125 and 15 minute dwelling period. 40 cycle was 3100. So this is what we designed this this thing BGS, and based on this PD 50/50, that means median time from canary to median time for the standard component, it was estimated to be 900 cycle. For use condition, it extends to that is use condition, that is from 60 to 80 degrees centigrade range. It was 48 minutes, 40-minute dwell time. The PD 50/50 improves to 22,800. Okay, if I go from the one temperature range to another temperature range, and if I have dwelling time of 480 minutes, the 50/50 matrix, PD matrix goes to 22. You can see we got that so many cycles it can work. So these are called design approach for canaries. And then week 5, let's say an overview. Physics of failure approach and introduction we had. We had an overview of electronics reliability, life cycle aspects that we saw. Then in the second lecture, exclusively we discussed failure mode, mechanism and effect analysis, saying that it is one of the family member of FMEA. The role of FMEA in physics of failure we explored, and we demonstrated it is a very effective way for POF. FMEA procedural element we saw, POF failure models we saw, fatigue we discussed thermal solder fatigue, and metallization of course was part of it because of CTE or only temperature alone. Okay, those properties, and fatigue failure models that we saw in terms of damage DI, PHM and POF. Then cumulative damage thing we saw, and cumulative damage model also we discussed. Then life consumption monitoring, and then last canary and prognostics, background prognostic, distance, error seeding, beautiful mechanism to develop a canary, and illustration of canary approach. So logically we started from introduction, and we have gone to illustration of canary approach, and we in between we saw some opportunity to learn about electronic component, and as and when it was possible we have given transistor, then we have given MOSFET little understanding, and one of the slides we discussed various electronic component, their function, how they are represented. So that means in a way we are gearing up for a POF for electronics, and that should be a very good sign for us, that we have started working in an area where the heart of the system is trying to pump blood for big industries and all, because electronics form the core of the any system for its smooth functioning and even for safety also. Thank you.